There is something at the center of every black hole that should not be there, not because it is strange, not because it is dangerous, but because, according to the deepest principles of physics, it is impossible. It is called the singularity, and it is a point where the density of matter is infinite, the curvature of spacetime is infinite, and the volume of space is zero. A point where the mathematics of our best theory of gravity, general relativity, the most precise and beautiful theory ever written about the nature of space and time, produces an answer that is physically meaningless. An answer of infinity. And in physics, an answer of infinity is not an answer at all. It is a breakdown, a failure, a confession that the theory has been pushed beyond its limits and can no longer describe what is happening. Every black hole has a singularity at its center. Every one. According to current scientific estimates, the observable universe contains on the order of 100 billion galaxies. Nearly every large galaxy harbors a supermassive black hole at its center. Our Milky Way has Sagittarius A star, with roughly 4 million solar masses. The galaxy Messier 87 has one with 6.5 billion solar masses. The galaxy Ton 618 has one estimated at 66 billion solar masses. Beyond the supermassive, there are hundreds of millions of stellar mass black holes scattered through every galaxy, the remnants of massive stars that collapsed when their nuclear fuel ran out. Everywhere we look, in every direction, at every scale, singularities are there, points where physics breaks down, points that should not exist. And yet general relativity demands that they do exist. The Penrose-Hawking singularity theorems, proven in the mid-1960s, demonstrate that under very general physical conditions, singularities are inevitable consequences of gravitational collapse. Not possible, not occasional, inevitable. Once enough matter collapses past a certain threshold, once a trapped surface forms, the singularity must follow. No force can prevent it. No asymmetry can avoid it. No cleverness can circumvent it. The mathematics guarantees it. But quantum mechanics, the other great pillar of modern physics, says this cannot be right. The Heisenberg uncertainty principle forbids the compression of matter into zero volume. Unitarity, the principle that quantum evolution is always reversible and information is never destroyed, forbids the kind of breakdown that a singularity represents. Quantum mechanics is the most precisely tested theory in the history of science, verified to more than 12 decimal places of accuracy. If it says infinite density is impossible, that claim carries enormous weight. So we have a contradiction. General relativity says the singularity must exist. Quantum mechanics says it cannot. Both theories are extraordinarily well tested. Both are extraordinarily successful in their own domains. And they cannot both be right about the center of a black hole. One of them, or perhaps both, must be wrong at the singularity. And figuring out which one gives way, and what replaces the singularity when it does, is the most important unsolved problem in all of physics. The singularity is also personal in a way that other physics problems are not. It is a question about what would happen to you, to your body, your consciousness, your experience, if you fell into a black hole. General relativity provides a detailed answer. You would cross the event horizon, fall for a finite time, and then be destroyed at the singularity. But quantum mechanics says the singularity cannot exist. So the general relativistic answer is wrong, and the correct answer, the quantum gravitational answer, is unknown. By the end of tonight, you are going to understand why general relativity predicts the singularity, why quantum mechanics forbids it, why this contradiction is the deepest crisis in modern physics, and what the leading proposals for resolving it look like. You are going to confront the possibility that space and time themselves are not fundamental, that they emerge from something deeper, and that the singularity is the point where the emergence fails and the deeper reality demands to be seen. Before we get started, if you find these mysteries as fascinating as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. The center of a black hole should not exist. That statement is not philosophical speculation. It is the conclusion of rigorous physics, supported by the two most successful theories in the history of science, theories that agree on virtually everything except the one place where they overlap most violently: the center of a black hole. The resolution of this contradiction will require a revolution in physics so profound that it will change our understanding of space, time, matter, and the nature of reality itself. The singularity is not just a problem, it is the problem, and every other mystery in physics, dark matter, dark energy, the unification of forces, the nature of consciousness, ultimately connects back to the same fundamental question that the singularity forces us to confront: what is spacetime made of? Consider the sheer scope of this problem. The singularity is not hiding in some remote, exotic corner of the universe. It is at the center of every large galaxy. It is in the remnants of every massive star that has ever died. It is in the products of every black hole merger that LIGO has detected. According to current models, the Milky Way alone may contain hundreds of millions of stellar mass black holes, each with a singularity at its center. The observable universe, with its 100 billion galaxies, contains a staggering number of these objects. The universe is not sprinkled with singularities, it is saturated with them, and each one is a point where our understanding of reality completely fails. The singularity is also connected to the most fundamental questions about the origin and structure of the cosmos. Many cosmological models predict an initial singularity at the very beginning of cosmic history, a moment of infinite density analogous to the singularity at the center of a black hole. If the black hole singularity is resolved by quantum gravity, the initial singularity may be resolved by the same mechanism. The fate of the center of a black hole and the origin of the universe may be the same problem, viewed from different temporal perspectives. Now, let us begin. To understand why the center of a black hole should not exist, we must first understand the theory that predicts it. We must understand general relativity, its extraordinary successes, and the precise mechanism by which it produces the singularity. Because the singularity is not an accident. It is not a mistake in the calculation. It is a direct, unavoidable consequence of the most fundamental principles of the theory, and appreciating why it arises is the first step toward understanding why it must be wrong. General relativity, published by Albert Einstein in 1915, is a theory of gravity, but it is unlike any theory of gravity that preceded it. In Newton's framework, which reigned for more than 2 centuries, gravity is a force that acts instantaneously between two masses across empty space. The sun pulls the earth pulls the moon. The force depends on the masses and the distance between them. This picture works extraordinarily well for everyday situations. It sent astronauts to the moon. It predicts the tides. It describes the orbits of planets with high precision. But Newton's gravity has a fatal flaw. The force acts instantaneously. If the sun vanished, Newton's theory says the Earth would immediately feel the absence, even though light from the sun takes roughly 8 minutes to reach us. This contradicts special relativity, Einstein's earlier theory from 1905, which establishes that no influence, no signal, no information of any kind can travel faster than the speed of light. Einstein resolved this contradiction by reimagining gravity completely. In general relativity, gravity is not a force, it is the curvature of spacetime. Mass and energy curve the fabric of space and time, and objects move along the straightest possible paths through that curved geometry. The Earth does not orbit the Sun because the Sun pulls on it. The Earth orbits because the Sun has warped the spacetime around it into a curved geometry, and the Earth follows the natural paths through that geometry. These paths are called geodesics, and they are the general relativistic equivalent of straight lines. The mathematics of general relativity is encoded in Einstein's field equations, 10 coupled, nonlinear, partial differential equations that relate the geometry of spacetime, described by the metric tensor, to the distribution of mass and energy, described by the stress-energy tensor. These equations are extraordinarily difficult to solve exactly, but the solutions that have been found are among the most important achievements in the history of physics. The first exact solution was found by Karl Schwarzschild in 1916 within months of Einstein's publication. Schwarzschild was serving on the Eastern Front of the First World War, suffering from a fatal autoimmune disease called pemphigus. Despite these conditions, he solved Einstein's equations for the simplest case, a perfectly spherical, non-rotating, uncharged mass. His solution described the spacetime geometry around such an object with perfect mathematical precision. The Schwarzschild solution contains two special radii. The first is the Schwarzschild radius, the radius of the event horizon, the boundary beyond which nothing can escape. The second is the origin, the center, where the mathematics produces infinity. The curvature diverges, the density diverges, the tidal forces diverge. Every physical quantity that the theory can compute becomes infinite at this point. This is the singularity. The Schwarzschild radius for any object depends only on its mass. For our Sun, it is approximately 1.86 miles. For the Earth, it is approximately 9 millimeters. For a human being of 70 kilograms, it is roughly 10 to the power of negative 25 meters, far smaller than a proton. These numbers tell us that ordinary objects are nowhere near compact enough to form black holes. The Sun's actual radius is roughly 432,000 miles, more than 200,000 times its Schwarzschild radius. To make the Sun into a black hole, you would need to compress it by a factor of more than 200,000, crushing all its matter into a sphere less than 4 miles across. For decades after Schwarzschild's discovery, most physicists assumed this compression was physically impossible. The singularity was dismissed as a mathematical curiosity, an artifact of the unphysical perfection of the Schwarzschild solution. Real stars are not perfectly spherical. Real collapses are messy and turbulent. Surely the asymmetries would prevent the collapse from reaching infinite density. The great British astronomer Arthur Eddington was openly hostile to the idea of gravitational collapse to a singularity. When the young Indian physicist Reinhard Chandrasekhar presented his calculation showing that white dwarfs above roughly 1.4 solar masses must collapse further, Eddington publicly ridiculed him. Einstein himself was skeptical that nature would permit such objects. But the physics was relentless. In the 1930s, Chandrasekhar established the upper mass limit for white dwarfs. Fritz Zwicky and Walter Baade proposed the existence of neutron stars, objects supported by the pressure of neutrons rather than electrons, but even neutron stars have an upper mass limit of roughly 3 solar masses. Above that limit, there is no known force that can prevent further collapse. In 1939, J. Robert Oppenheimer and Hartland Snyder published a paper showing that a sufficiently massive star, once it exhausts its nuclear fuel, will collapse without end. The core contracts, the density rises, the Schwarzschild radius is crossed, and the matter continues to fall inward. The equations of general relativity predict that the collapse proceeds to a singularity, a point of infinite density and zero volume. Oppenheimer and Snyder showed that this is not a theoretical possibility, but a physical inevitability for stars above a certain mass. Gravity always wins. The process of stellar collapse that creates black holes is one of the most violent events in nature. A star 25 or more times the mass of the Sun burns through its nuclear fuel in a few million years. When the fuel is exhausted, the outward pressure from nuclear fusion ceases, and the core collapses under its own gravity. The collapse happens in less than a second. The outer layers of the star, falling inward and then rebounding off the hardening core, are blasted outward in a supernova explosion. For a few weeks, a single supernova can outshine an entire galaxy of hundreds of billions of stars. The energy released is roughly 10 to the power of 46 joules, more energy in a few seconds than the Sun will emit in its entire lifetime. The elements scattered by the supernova, iron, gold, uranium, carbon, oxygen, are the raw materials from which planets and eventually life are assembled. The atoms in our bodies were forged in stars that died this way. Many of those stars left behind black holes. The singularities at the centers of those black holes are the dark siblings of the elements that make us. If the remaining core exceeds roughly 3 solar masses, no known force can halt the collapse. The matter contracts past the Schwarzschild radius. The event horizon forms. And the equations of general relativity predict that the collapse continues without end, to a point of infinite density. a singularity. The term black hole was popularized in 1967 by John Archibald Wheeler. Before Wheeler, these objects were called frozen stars or collapsed stars. Wheeler's term captured the public imagination because it was vivid and accurate. A black hole is black because no light escapes. It is a hole because nothing that enters ever returns. The discovery that changed everything came in 1965, when Roger Penrose proved his singularity theorem. Before Penrose, there was still hope that the singularity was an artifact of the perfect symmetry assumed in the Schwarzschild solution. Penrose destroyed that hope. His theorem showed that singularities are unavoidable consequences of general relativity under very general conditions. The proof required only three assumptions: that general relativity is correct, that the energy density of matter is positive, and that a trapped surface has formed. A trapped surface is a closed, two-dimensional surface from which all outgoing light rays are converging inward, a condition that is always satisfied inside an event horizon. Once these conditions are met, Penrose showed, geodesic incompleteness must follow. There must be world lines that terminate after a finite proper time. There must be a singularity. Penrose's proof was topological, using mathematical techniques from differential geometry that had never before been applied to general relativity. It was elegant, general, and devastating. No amount of asymmetry, no amount of rotation, no amount of turbulence or perturbation can prevent the singularity. The theorem is robust. It depends on very mild assumptions, and it guarantees that the singularity forms. Stephen Hawking recognized the power of Penrose's method and extended it. Together they proved more general singularity theorems in the late 1960s. Penrose received a share of the Nobel Prize in Physics in 2020 for this work. Einstein's field equations are deceptively simple in their tensor notation but extraordinarily complex in their content. The equations relate the Einstein tensor, which encodes the curvature of spacetime, to the stress-energy tensor, which encodes the distribution of mass and energy. In component form, they are 10 independent equations for 10 independent components of the metric tensor, the mathematical object that describes the geometry of spacetime at every point. Solving these equations exactly requires either high symmetry or extraordinary mathematical ingenuity. The Schwarzschild solution assumes perfect spherical symmetry and a vacuum exterior, meaning no matter outside the central mass. Despite these simplifications, the solution captures the essential physics of gravitational collapse and predicts both the event horizon and the singularity with mathematical precision. The success of the Schwarzschild solution in predicting observable effects, the bending of light, the precession of Mercury, gravitational time dilation, is what makes the failure at the singularity so jarring. The same equations that work perfectly at moderate curvatures produce nonsense at extreme curvatures. The Schwarzschild radius has a simple proportionality to mass. Double the mass, double the radius. This means the average density of a black hole at its event horizon decreases as mass increases. For a solar mass black hole, the average density at the horizon is billions of kilograms per cubic centimeter. For a supermassive black hole of 10 billion solar masses, the density at the horizon is less than the density of water. You could cross the event horizon of a sufficiently large supermassive black hole and find yourself in a region less dense than the ocean, and yet you would be inside a black hole, falling inexorably toward the singularity. The density at the Schwarzschild radius provides an instructive comparison across different mass scales. For a stellar mass black hole of 10 solar masses, the average density at the event horizon is roughly 200 million tons per cubic centimeter. For Sagittarius A star, with 4 million solar masses, the density at the horizon is roughly 1,000 kilograms per cubic centimeter, comparable to the density of a heavy metal. For M87 star, with 6.5 billion solar masses, the density at the horizon is less than the density of Earth's atmosphere at sea level. The larger the black hole, the more diffuse the matter at its boundary. You could cross the horizon of M87 star surrounded by spacetime, less dense than the air you are breathing right now, and the singularity at the center would still be there, according to general relativity, waiting at the end of every possible path. This inverse relationship between size and boundary density is one of the most counterintuitive features of black holes. The most massive black holes have the most gentle event horizons. You would notice nothing unusual when crossing, no alarm, no force, no indication that you had just passed the point of absolute no return. The gentleness of the entry makes the violence of the destination all the more disturbing. The door through which you enter is silent. The room to which you are delivered is the most violent place in the universe. The journey from the event horizon to the singularity has been computed in detail for Schwarzschild black holes. The proper time, the time measured by the falling observer's own clock, depends on the mass and on the initial conditions of the fall. For a free fall from rest at the event horizon of Sagittarius A star, the time to the singularity is roughly 20 seconds. During those seconds, the tidal forces grow from negligible to infinite. The geometry contracts around the observer. The perpendicular spatial dimensions squeeze inward. The dimension along the fall stretches. The BKL oscillations set in near the center, the geometry convulsing chaotically in patterns of increasing frequency and violence. For the most massive known black holes, with masses exceeding 10 billion solar masses, the time from the event horizon to the singularity could extend to many hours. This raises the profound and disturbing possibility of prolonged consciousness inside a black hole, hours of awareness inside a region from which no escape is possible, falling toward a destination that physics cannot describe. The observer would have time to conduct experiments, make observations, record data, and none of that data could ever reach the outside universe. The event horizon ensures that the only witnesses to the breakdown of physics are witnesses who can never testify. The Kerr solution for rotating black holes reveals a more complex interior. Found by Roy Kerr in 1963, the Kerr metric describes a black hole with angular momentum. The interior has two horizons and a ring-shaped singularity. The Kerr mathematics formally permits paths through the ring into different spacetimes. But the inner Cauchy horizon is almost certainly unstable, destroyed by the mass inflation instability demonstrated by Werner Israel and Eric Poisson. The elegant Kerr interior is a mathematical idealization that does not survive in realistic conditions. The cosmic censorship conjecture, proposed by Penrose in 1969, states that singularities are always hidden behind event horizons. If this conjecture holds, the breakdown of physics at the singularity is quarantined, contained within the black hole, unable to affect the outside universe. The event horizon also has deep implications for what we can know about the singularity. Because no information can escape from inside the event horizon, the singularity is permanently shielded from observation. We can observe the exterior of black holes with extraordinary precision, photographing their shadows, detecting their gravitational waves, tracking the orbits of stars around them. But the interior, including the singularity, is forever beyond the reach of any observation. The universe has placed the proof of the incompleteness of our theories behind an impenetrable wall. This wall, the event horizon, is the most absolute boundary in nature. Nothing crosses it outward. No light, no matter, no information, no signal of any kind. The singularity is the most important thing we cannot see, the most important thing we cannot measure, the most important thing our theories cannot describe. It is the cosmic Rosetta Stone, the key to translating between the language of gravity and the language of quantum mechanics, the cipher that, once cracked, will unlock the deepest structure of the universe. It is the blind spot in our understanding of the cosmos, the gap at the center of the map, the missing piece in the puzzle of reality. And yet we know it is there. We know it because our equations predict it. We know it because the Penrose-Hawking theorems guarantee it. We know it because every alternative, every attempt to avoid it within the framework of general relativity, fails. The singularity is the unavoidable consequence of the theory that predicts it, and the most powerful argument for replacing that theory with something better. This observational inaccessibility means that everything we know about the singularity comes from theory, and the theory, at the singularity, produces infinity. We cannot test our predictions because we cannot observe the singularity, and we cannot trust our predictions because the predictions are infinite. We are doubly blind, unable to see the singularity and unable to calculate what it is. Every black hole we have ever observed, from the first stellar mass candidate in Cygnus zone to the most recent gravitational wave detection, is consistent with the predictions of general relativity for the exterior. Not a single observation has contradicted the theory outside the event horizon. This extraordinary success makes the failure at the center all the more striking. The same equations that predict the bending of starlight to 6 significant figures, that predict gravitational wave frequencies to 14 significant figures, that predict the shadow of M87 star to the precision of the Event Horizon Telescope, these same equations predict infinite density at the center. The theory is simultaneously the most precise and the most wrong of any theory in history. It is perfect everywhere, except at the one point that matters most. The resolution of the singularity will require a theoretical breakthrough, a new theory of quantum gravity that produces finite predictions where general relativity produces infinities. But cosmic censorship has never been proven in full generality. Its truth or falsity remains one of the great open problems in mathematical physics. If cosmic censorship fails, naked singularities could form, singularities visible to the outside universe, with catastrophic implications for determinism and predictability. This contrast between the gentleness of the horizon and the violence of the singularity encapsulates the entire problem. General relativity describes the gentle part perfectly. It fails at the violent part. The theory works in the regime of moderate curvature and breaks down in the regime of extreme curvature, and the breakdown is not gradual, it is total. The equations go from producing meaningful, testable predictions to producing meaningless infinities in a single step. The proper time from the event horizon to the singularity is finite and depends on the black hole's mass. For Sagittarius A star, this time is roughly 20 seconds. For M87 star, it could be hours. During this time, the falling observer would experience the contraction of spatial dimensions perpendicular to the fall, the stretching of the dimension along the fall, the growing tidal forces, the increasingly chaotic BKL oscillations, and finally the approach to infinite curvature at the singularity. The journey from the event horizon to the singularity is a journey from the known to the unknown, from the regime where physics works to the regime where it fails. Now consider the observational evidence that these objects actually exist. In 1971, the X-ray binary system's Cygnus zone was identified as a strong black hole candidate, with a compact object too massive to be a neutron star. In 2015, the LIGO Observatory detected gravitational waves from the merger of two black holes, designated GW150914, confirming the existence of black holes through an entirely new observational channel. The two black holes had masses of roughly 36 and 29 solar masses, and their merger produced a final black hole of 62 solar masses, with the missing 3 solar masses converted entirely into gravitational wave energy. The peak luminosity during the merger exceeded the combined light output of every star in the observable universe. In 2019, the Event Horizon Telescope captured the first direct image of a black hole's shadow, the silhouette of M87 star against its glowing accretion disk. In 2020, Andrea Ghez and Reinhard Genzel shared the Nobel Prize for tracking individual stars orbiting Sagittarius A star for more than 2 decades, demonstrating that the central object has 4 million solar masses compressed into a region smaller than our solar system. In 2022, the EHT released an image of Sagittarius A star itself. The implications of the Penrose-Hawking singularity theorems cannot be overstated. They showed that Einstein's theory, the most elegant and successful theory of gravity ever conceived, contains within its own equations the seeds of its own destruction. The theory predicts singularities, and at those singularities, the theory fails. It predicts the conditions under which its own predictions become meaningless. It is as if a map contained, at its very center, the words, "This map is no longer accurate." The map works everywhere else, but at the center, it admits its own inadequacy. The theorems also closed the door on the hope that singularities could be avoided by realistic conditions. Before Penrose, physicists could hope that the real universe, with all its messiness and asymmetry, would find a way around the singularity. After Penrose, that hope was gone. The singularity is not a consequence of idealization. It is a consequence of the basic structure of general relativity combined with the basic physical assumption that energy is positive. To avoid singularities, you must change the theory. You must introduce new physics that operates at extreme curvatures and prevents the collapse from reaching infinite density. And that new physics must come from quantum gravity, a theory that does not yet exist. Between Penrose's original theorem and the present, the singularity has been studied by thousands of physicists using every available mathematical tool. Every study has confirmed the basic result. Under general conditions, singularities are inevitable in general relativity. The universe, according to our best theory of spacetime, contains points where that theory fails, and those points are not rare. They are everywhere. Since the first LIGO detection, roughly 90 gravitational wave events have been observed, the majority from black hole mergers. Each event tests general relativity in the strong field regime. The waveforms match theoretical predictions with extraordinary accuracy. The ring-down signals, produced when the merged black hole vibrates like a struck bell, confirm the no-hair theorem. The final object is consistent with a Kerr black hole characterized by just mass and spin. To appreciate the scale of these objects, consider some comparisons. A stellar mass black hole of 10 solar masses has a Schwarzschild radius of roughly 18.5 miles. The density implied by compressing 10 solar masses into that volume is roughly 200 million tons per cubic centimeter. A single teaspoon would weigh as much as a mountain range. The tidal forces at the event horizon are extreme, strong enough to spaghettify a human body before it crosses the boundary. For supermassive black holes, the event horizon is vastly larger. Sagittarius A star's event horizon has a radius of roughly 7.5 million miles. M87 star's event horizon diameter is roughly 24 billion miles, larger than the orbit of Pluto. The black hole in Phoenix A, reported in 2022, has roughly 100 billion solar masses and an event horizon that would swallow our entire solar system. Paradoxically, the larger the black hole, the gentler the event horizon. The tidal forces at the horizon decrease as mass increases. You could cross the event horizon of a sufficiently large supermassive black hole without feeling anything unusual. No pain, no warning, no indication that you had crossed the point of no return. And inside, you would have seconds, minutes, or even hours of conscious experience before the tidal forces grew to lethal intensity near the center. The time between crossing the event horizon and reaching the singularity depends on the black hole's mass. For Sagittarius A star, it is roughly 20 seconds. For the most massive known black holes, it could be hours inside a black hole, falling toward a singularity that general relativity says must be there, but quantum mechanics says cannot be. And at the center, the singularity waits, infinite density, zero volume, the end of physics. The no-hair theorem, proven through a series of results in the 1960s and 70s, states that a black hole is completely characterized by just three quantities: its mass, its charge, and its angular momentum, nothing else. No matter what form the black hole, no matter how complex the progenitor star, no matter what the chemical composition or structure of the infalling matter, the final black hole remembers only three numbers. All other information is hidden behind the event horizon, presumably compressed toward or near the singularity. This radical simplicity of the exterior is the mirror image of the radical complexity of the interior. The fewer details the outside reveals, the more details must be hidden inside. The Bekenstein-Hawking entropy, proportional to the area of the event horizon, tells us that the internal complexity is enormous. For a solar mass black hole, the entropy is roughly 10 to the power of 77. For Sagittarius A star, it is roughly 10 to the power of 87. These numbers represent the number of microscopic configurations the black hole can occupy while looking identical from the outside. The singularity, if it exists, must somehow accommodate this vast complexity. And a true singularity, a point of infinite density and zero volume, cannot accommodate anything. It is a mathematical abstraction with no physical content. There is also the photon sphere, located at 1.5 Schwarzschild radii, where light can orbit the black hole. The visual distortions near a black hole are extreme, bending and multiplying images of distant stars, creating rings and arcs of light. These effects, while spectacular, are consequences of the same curvature that, at the center, becomes infinite and produces the singularity. The gentle bending of light at the photon sphere and the infinite curvature at the center are related by the same equations. The theory works beautifully at the photon sphere. It fails completely at the center. Inside the event horizon, the nature of spacetime changes fundamentally. The radial coordinate becomes timelike. The singularity is not at the center in any spatial sense. It is in the future. And every path inside the black hole leads to the singularity, not because it is in every direction in space, but because it is in the one direction that cannot be avoided, the future. The falling observer is not traveling toward a place. They are aging toward a moment, and that moment, according to general relativity, is the moment of infinite density. The BKL dynamics, discovered by Vladimir Belinsky, Isaac Kalatnikov, and Evgeny Lifshitz, describe how spacetime behaves near the singularity. The geometry oscillates chaotically, contracting in one direction while expanding in another, the pattern changing faster and faster as the singularity is approached. Charles Misner called this mix-master dynamics. The approach to the singularity is not gentle or orderly. It is violent, chaotic, and increasingly frenzied. The geometry writhes and convulses in patterns of ever-increasing complexity and frequency. For a rotating black hole, described by the Kerr solution found by Roy Kerr in 1963, the interior is even more complex. The Kerr black hole has two horizons, an outer event horizon and an inner Cauchy horizon. The singularity takes the form of a ring rather than a point. The Kerr mathematics formally permits paths through the ring into what the equations describe as entirely different spacetimes, but the inner Cauchy horizon is almost certainly unstable. The mass inflation instability, demonstrated by Werner Israel and Eric Poisson, shows that infalling radiation is blue-shifted to arbitrarily high energies at the inner horizon, replacing it with a singularity. The beautiful Kerr interior, with its ring singularity and alternate universes, is almost certainly a mathematical idealization that does not survive contact with reality. But here is the problem. Every principle of quantum mechanics says this cannot be right. The core problem with the center of a black hole is not merely that the mathematics produces infinity, it is that the singularity violates virtually every fundamental principle of quantum mechanics, the other great pillar of modern physics. Understanding this violation in detail is essential, because it reveals that the singularity is not just a technical problem to be fixed. It is a conceptual crisis that demands a revolution in our understanding of reality. Let us examine, one by one, the principles that the singularity violates. The first is the Heisenberg uncertainty principle. This principle, one of the cornerstones of quantum mechanics, states that certain pairs of physical quantities, such as position and momentum, cannot be simultaneously known with arbitrary precision. The more precisely you know the position of a particle, the less precisely you can know its momentum, and vice versa. The product of the two uncertainties can never be less than a fixed minimum value, Planck's reduced, constant divided by 2. The singularity violates this principle directly. At the singularity, all matter is compressed into zero volume. This means the position of every particle is known with infinite precision. It is at the singularity, at the point of zero volume. But the uncertainty principle says that if the position is known with infinite precision, the uncertainty in momentum must be infinite. Infinite momentum implies infinite kinetic energy. An infinite kinetic energy implies a pressure that resists further compression. The quantum mechanical pressure generated by the uncertainty principle should prevent matter from being compressed to infinite density. The singularity, according to quantum mechanics, is impossible. This is not a vague, hand-waving argument. It can be made quantitative. When matter is compressed to densities approaching the Planck density, roughly 5.1 times 10 to the power of 96 kilograms per cubic meter, the quantum uncertainty in particle positions becomes comparable to the Planck length, roughly 10 to the power of negative 35 meters. At this point, the quantum pressure becomes comparable to the gravitational pressure. The compression should halt. The density should plateau at the Planck density, an enormous number, but critically not infinity. The singularity should be replaced by a Planck scale core, a region of extreme but finite density. This argument, while heuristic, is supported by every candidate theory of quantum gravity. String theory provides a minimum length, the string length. Loop quantum gravity provides a minimum volume, the Planck volume. Causal set theory provides a minimum spacetime element. In each case, the quantum structure of spacetime prevents the compression from proceeding to infinite density. The singularity is halted at the Planck scale, replaced by a region of extreme but finite density. The Planck density, roughly 5.1 times 10 to the power of 96 kilograms per cubic meter, is an enormous number. It is roughly 78 orders of magnitude greater than nuclear density, which is itself roughly 10 to the power of 18 kilograms per cubic meter. But it is not infinity. And the distinction between enormously large and infinite is the distinction between a theory that makes physical sense and one that does not. A cube of matter at the Planck density with a side length of 1, Planck length would have a mass of roughly 22 micrograms, roughly the mass of a grain of sand. This tiny Planck scale grain would be the densest possible configuration of matter, the quantum gravitational equivalent of a maximum packing. The singularity is replaced by the smallest, densest grain of matter that the laws of physics permit. The second violated principle is unitarity. Unitarity is the statement that quantum mechanical evolution is always reversible. If you know the quantum state of a system at one time, you can determine its state at any other time, past or future. Information is never created. Information is never destroyed. No, the total probability of all possible outcomes always adds up to 1. The quantum state always evolves from a pure state to another pure state, never from a pure state to a mixed state without an accompanying loss of coherence that can be tracked and, in principle, reversed. The singularity violates unitarity because it destroys information. Matter falls into the black hole, reaches the singularity, and the information encoded in that matter, the precise quantum state of every particle, is compressed into a point of infinite density where the equations produce infinity and the physics breaks down. The information does not emerge on the other side because there is no other side. The singularity is the end of the road. The information is gone. This violation became dramatically concrete in 1974 when Stephen Hawking showed that black holes emit thermal radiation, now called Hawking radiation. This radiation arises from quantum effects near the event horizon. Virtual particle-antiparticle pairs, constantly created and annihilated in the quantum vacuum, are separated by the extreme curvature near the horizon. One particle falls in, the other escapes. The black hole loses mass. Over unimaginably long timescales, the black hole evaporates completely. The Hawking radiation is thermal. It is featureless. It carries no information about what fell into the black hole. A black hole formed from the collapse of a star made of pure hydrogen emits exactly the same radiation as a black hole of identical mass formed from a star made of pure iron. Every detail, every nuance, every quantum number of the infalling matter is erased. If the black hole evaporates completely and the radiation carries no information, then the information is permanently destroyed. This is the black hole information paradox, and it has consumed the attention of theoretical physicists for more than 50 years. The depth of this crisis cannot be overstated. Unitarity is not a minor feature of quantum mechanics. It is a structural pillar. Every prediction quantum mechanics has ever made relies on unitarity. Quantum computing relies on it. The standard model of particle physics relies on it. The theory of quantum electrodynamics which predicts the anomalous magnetic moment of the electron to more than 12 decimal places of accuracy, relies on it. If unitarity fails at the singularity, the repercussions cascade through all of physics. Most physicists now believe that unitarity is preserved during black hole evaporation. That information is not destroyed. Hawking himself conceded a bet with John Preskill in 2004, acknowledging that information is likely preserved. But if unitarity is preserved, then the singularity cannot be what general relativity says it is. Something must happen at or near the center that preserves information rather than destroying it. Something must replace the singularity. The information paradox connects directly to the singularity because the two problems are inseparable. If the singularity is where information ends up, and if the singularity is a point of infinite density where physics breaks down, then the information is effectively destroyed. But if the singularity is replaced by something finite, something quantum gravitational, something that preserves the structure of quantum mechanics, then information may be preserved. The resolution of the singularity and the resolution of the information paradox are the same problem viewed from different angles. The island formula, developed in 2019 and 2020, showed that the entropy of Hawking radiation follows the Page curve, confirming within certain models that information is preserved during black hole evaporation. This result strongly implies that the singularity does not destroy information. Whatever replaces the singularity in the full quantum theory preserves unitarity and returns information to the outside universe through the Hawking radiation. The island formula does not tell us what replaces the singularity, but it constrains the replacement. It must be consistent with unitary evolution. It must be consistent with the Page curve. It must preserve information. Hawking radiation itself connects to the thermodynamics of black holes in ways that further constrain the singularity. The Hawking temperature of a black hole is inversely proportional to its mass. For a solar mass black hole, the Hawking temperature is roughly 60 billionths of a Kelvin, far colder than the cosmic microwave background. The evaporation time is roughly 10 to the power of 67 years, exceeding the current estimated age of the universe by a factor of more than 10 to the power of 56. For a supermassive black hole of 10 billion solar masses, the evaporation time stretches to roughly 10 to the power of 100 years, a Google. The tension between general relativity and quantum mechanics at the singularity is not a minor inconsistency. It is a head-on collision between two frameworks that have been independently verified to extraordinary precision. General relativity has been confirmed by gravitational wave observations, by the imaging of black hole shadows, by the precession of stellar orbits, by the bending of light, by gravitational time dilation measured on satellites and aircraft. Quantum mechanics has been confirmed by atomic spectroscopy, by the anomalous magnetic moment of the electron, by quantum electrodynamics, by the standard model of particle physics, by the operation of semiconductors and lasers and superconductors. Both theories work. Both have been tested to incredible accuracy, and they contradict each other at the singularity. The depth of this contradiction makes the singularity the most important problem in physics. Resolving it will not merely fix a local problem at the center of a black hole. It will reveal the deep structure of reality. It will tell us what spacetime is made of. It will connect gravity to quantum mechanics in a unified framework. It will answer questions that have been open since Einstein first wrote down his field equations. The theory of quantum gravity that resolves this contradiction must satisfy extraordinarily stringent demands. It must agree with general relativity wherever general relativity has been tested, which is to say at all curvatures up to and including those near the event horizons of merging black holes. It must agree with quantum mechanics wherever quantum mechanics has been tested, which is to say at all energy scales up to and including those probed by the Large Hadron Collider. And it must produce finite, well-defined predictions at the Planck scale, where both theories fail. The conflict between general relativity and quantum mechanics at the singularity is the sharpest version of a tension that pervades all of modern physics. General relativity treats spacetime as smooth, continuous, and classical. Quantum mechanics treats physical systems as discrete, probabilistic, and subject to uncertainty. In most of physics, these two frameworks do not overlap. General relativity describes the large-scale structure of the cosmos, quantum mechanics describes the small-scale behavior of atoms and particles. They operate in different regimes, they use different mathematics, they answer different questions, but at the singularity, both regimes overlap violently. The mass is so concentrated that gravity is extreme, demanding general relativity. The scale is so small, approaching the Planck length, that quantum effects must be important, demanding quantum mechanics. And the two frameworks, when applied simultaneously, produce contradictions so severe that one or both must give way. The Planck scale is the natural arena for this confrontation. The Planck length, formed from Newton's gravitational constant, the speed of light, and Planck's reduced constant, is roughly 10 to the power of negative 35 meters. The Planck mass is roughly 22 micrograms. The Planck density is roughly 5.1 times 10 to the power of 96 kilograms per cubic meter. At these scales, quantum gravitational effects dominate. The smooth spacetime of general relativity dissolves into quantum foam. And the singularity, which general relativity predicts at zero volume and infinite density, is expected to be replaced by a Planck-scale quantum core of finite volume and enormous but finite density. The gap between the Planck scale and our experimental reach is one of the defining challenges of modern physics. The smallest distances we can probe with current technology are roughly 10 to the power of negative 18 meters, 17 orders of magnitude larger than the Planck length. The highest energies we can achieve are roughly 10 to the power of 4 giga-electron-volts, 15 orders of magnitude below the Planck energy. No foreseeable technology will bridge this gap through direct experiment. The study of the singularity must proceed through theory, through mathematical consistency, through astrophysical observations that provide indirect constraints, and through the patient accumulation of evidence from every available source. The connection between the singularity and quantum computation provides another perspective. Black holes are the fastest information scramblers in nature, saturating the fundamental quantum bound on scrambling speed. For Sagittarius A star, the scrambling time is on the order of milliseconds. The Margulis-Levitin theorem sets the maximum rate at which any quantum system can evolve between orthogonal states, and black holes operate at this limit. The singularity, or whatever replaces it, is the computational engine that drives this maximum rate processing. The center of the black hole is not a point of destruction, but a point of maximum computational activity. The Planck scale is defined by three fundamental constants: Newton's gravitational constant, the speed of light, and Planck's reduced constant. The Planck length is roughly 10 to the power of negative 35 meters. The Planck time is roughly 10 to the power of negative 43 seconds. The Planck mass is roughly 22 micrograms. The Planck density is roughly 5.1 times 10 to the power of 96 kilograms per cubic meter. These quantities define the natural scales of quantum gravity. At these scales, gravitational effects and quantum effects are of comparable importance. At these scales, the singularity is expected to be resolved. The gap between our experimental capabilities and the Planck scale is staggering. The smallest distances probed by the Large Hadron Collider are roughly 10 to the power of negative 18 meters, 17 orders of magnitude larger than the Planck length. The highest energies achieved are roughly 10 to the power of 4 giga-electron-volts, 15 orders of magnitude below the Planck energy. Bridging this gap through direct experiment would require an accelerator roughly a light-year in diameter. No such instrument will ever be built. This means the resolution of the singularity cannot come from direct experiment. It must come from theory, from mathematical consistency, from the internal logic of the candidate theories. This is an unusual situation in physics. Most advances have come from the interplay between theory and experiment, each informing and correcting the other. At the singularity, we have only theory. The experiments are beyond our reach. The observations are blocked by the event horizon. We must rely on the power of mathematics and the constraints of consistency to guide us. The thermodynamic constraints are particularly powerful. The Bekenstein-Hawking entropy formula assigns a specific, finite entropy to every black hole. The Hawking temperature assigns a specific, finite temperature. The four laws of black hole mechanics assign specific, well-defined thermodynamic relationships. Any resolution of the singularity must be consistent with all of these. The thermodynamics provides an independent check on every proposal, an additional constraint that must be satisfied, an extra equation that must be balanced. This means the study of the singularity must proceed through theory, through mathematical consistency arguments, through astrophysical observations that provide indirect constraints, and through the internal logic of the candidate theories themselves. The singularity cannot be observed directly, because it hides behind the event horizon. It cannot be probed experimentally, because the Planck scale is too far from our reach. It can only be understood through the power of mathematical reasoning, constrained by the twin pillars of general relativity and quantum mechanics. These thermodynamic properties are not merely derived from general relativity. They connect gravity to quantum mechanics and thermodynamics in a single formula. The Bekenstein-Hawking entropy, S equals A over 4 in Planck units, is the Rosetta Stone of quantum gravity. It connects the area of the event horizon gravity to the entropy thermodynamics, to the Planck scale quantum mechanics. Any resolution of the singularity must be consistent with this formula. The thermodynamics provides a powerful constraint that eliminates many naive proposals. The third violated principle is the holographic bound. The Bekenstein bound, established by Jacob Bekenstein in the early 1970s, sets a maximum on the amount of information that can be contained in a given region of space. This maximum is proportional to the area of the boundary of the region, not its volume. The Bekenstein-Hawking entropy of a black hole is proportional to the area of its event horizon, measured in Planck units. For a solar mass black hole, the Bekenstein-Hawking entropy is roughly 10 to the power of 77. This is an enormous number, representing the number of microscopic quantum states the black hole can occupy. Any replacement for the singularity must be consistent with this entropy. It must have enough internal structure, enough microscopic degrees of freedom, to account for 10 to the power of 77 distinct configurations. This is an extraordinarily stringent constraint, and it eliminates many naive proposals for resolving the singularity. The fact that the entropy scales with area rather than volume is itself a profound clue. It suggests that the fundamental degrees of freedom of the black hole are on the surface, on the event horizon, not in the interior. The three-dimensional interior, including the singularity, may be less fundamental than the two-dimensional boundary. This is the holographic principle, and it suggests that the singularity is not a physical entity but a breakdown of a three-dimensional approximation, a failure of the geometric description that emerges from the more fundamental boundary physics. The fourth violated principle is the third law of thermodynamics, which states that the entropy of a system at absolute zero is a well-defined constant, typically zero. If the singularity had infinite density, its thermodynamic properties would be ill-defined, violating the third law. The Bekenstein-Hawking entropy formula, which assigns a finite, well-defined entropy to every black hole, is inconsistent with a true singularity. The thermodynamics demands that the internal structure of the black hole be finite and well-defined, not singular, and it gets worse. The fifth violated principle is the principle of cosmic censorship, which states that singularities formed by gravitational collapse are always hidden behind event horizons. This conjecture, proposed by Roger Penrose in 1969, has never been proven in full generality. If it is wrong, if naked singularities conform, the consequences are catastrophic. A naked singularity would be a point of infinite curvature visible to the entire universe. It would violate causality. The past would no longer uniquely determine the future. Determinism, the bedrock of physics, would crumble. The universe would become fundamentally unpredictable. Most physicists believe cosmic censorship holds in physically realistic situations, but the very fact that we cannot prove it, despite decades of effort, is a sign of how poorly we understand the singularity. If we had a theory of quantum gravity that resolved the singularity, cosmic censorship might follow as a consequence. The inability to prove cosmic censorship and the inability to resolve the singularity are two faces of the same problem. The sixth problem, and the one that connects all the others, is the conflict between general relativity and quantum mechanics at the Planck scale. General relativity is a classical theory. It treats spacetime as smooth, continuous, infinitely divisible. Quantum mechanics treats the physical world as discrete, probabilistic, and subject to uncertainty relations. At the Planck scale, where the curvature approaches the Planck curvature and the density approaches the Planck density, both theories are needed and neither works alone. General relativity ignores quantum effects. Quantum mechanics ignores gravity. The singularity is the place where this mutual ignorance produces catastrophe. The theory that would resolve this conflict is called quantum gravity. It would provide a unified framework that reduces to general relativity at large scales and to quantum mechanics at small scales, while remaining well-defined and producing finite predictions at all scales, including the Planck scale. Such a theory does not yet exist in a complete confirmed form. We have candidates, we have frameworks, we have partial results, but the final theory remains elusive. The situation is analogous to the ultraviolet catastrophe that confronted physics in the late 19th century. Classical electromagnetism and thermodynamics predicted that a hot object should radiate infinite energy at short wavelengths. This prediction was clearly wrong, and the resolution was quantum mechanics, an entirely new framework that replaced the classical description with something fundamentally different. The singularity may be the ultraviolet catastrophe of the 21st century. The resolution may require an equally radical departure from our current frameworks. Something is wrong with our assumptions about the nature of spacetime, not a small error, not a technical mistake. A deep fundamental flaw in the way we think about space, time, and the geometry of the universe, and the singularity is the proof. It is the clearest, most undeniable evidence that our current understanding of spacetime is incomplete. It is a mathematical theorem, proven rigorously by Penrose and Hawking, that the equations of general relativity produce infinity under conditions that are physically realized in every black hole. The proof is not hypothetical, it is not speculative, it is mathematical, logical, and airtight. The singularity must exist if general relativity is exactly correct, and the singularity cannot exist if quantum mechanics is exactly correct. Both cannot be exactly correct. One must be modified, and the modification, whatever it turns out to be, will be the theory of quantum gravity. But here is what makes this truly terrifying. The singularity sits behind the event horizon, shielded from observation by the one-way causal boundary that defines a black hole. We cannot observe it. We cannot probe it. We cannot send instruments to it and receive their data. The universe has placed the proof of our ignorance behind an impenetrable wall, visible only to those who fall through and forfeit the ability to report what they find. There is one more principle that the singularity violates, and it may be the most fundamental of all. It is the principle that physics should be deterministic, that the state of the universe at one time should uniquely determine its state at all future and past times. The singularity violates this because it is a geodesic incompleteness, a place where world lines simply end. If a particle reaches the singularity and its world line terminates, then the future of that particle is undefined. Physics cannot predict what happens because there is no future to predict. The chain of causation breaks. Determinism fails. In a deterministic theory, every event has a cause, and every cause has an effect. The singularity breaks this chain. It is an event with no future, a cause with no effect, a state with no successor. This is not just a technical problem, it is a philosophical crisis. If the universe contains points where determinism fails, then the universe is not fully predictable, even in principle. The fabric of causality has holes in it, and those holes are at the centers of billions of black holes scattered throughout the cosmos. Quantum mechanics provides a way to restore determinism, at least in a probabilistic sense. Quantum evolution is unitary, meaning the quantum state at one time uniquely determines the state at all other times. If the singularity is resolved by quantum gravity, determinism is restored. The world lines do not terminate. They pass through the Planck-scale quantum core and continue beyond it, perhaps into a white hole, perhaps into a different phase of spacetime. The chain of causation is preserved. The fabric of causality is mended. The universe becomes whole again. The holes in determinism are filled. And the center of the black hole, which should not exist as a singularity, is revealed as something finite, comprehensible, and consistent with all the principles of physics. The center of a black hole should not exist because every principle of quantum mechanics says it cannot, and yet general relativity says it must. The resolution of this paradox will not be a minor adjustment. It will be a revolution comparable to the birth of quantum mechanics or the formulation of general relativity. It will require new mathematics, new concepts, new ways of thinking about what space, time, and existence actually mean. And that revolution is already underway, driven by the singularity problem, fueled by the information paradox, guided by the holographic principle, and constrained by the thermodynamics of black holes. The Penrose process and the ergosphere of rotating black holes provide additional context. Roger Penrose showed in 1969 that energy can be extracted from a rotating black hole through its ergosphere, the region outside the event horizon where spacetime is dragged around by the black hole's rotation. For a maximally spinning black hole, up to roughly 29% of the total mass energy can be extracted. This reveals that black holes are not passive objects. They are dynamic thermodynamic systems with energy that can be tapped, entropy that can be measured, and temperatures that can be calculated. The singularity sits at the center of a thermodynamic engine, and any resolution of the singularity must be consistent with the engine's thermodynamic properties. The four laws of black hole mechanics, established by James Bardeen, Brandon Carter, and Stephen Hawking in the early 1970s, mirror the four laws of thermodynamics exactly. The zeroth law states that surface gravity is constant across the horizon. The first law relates mass changes to area, angular momentum, and charge changes. The second law states that total horizon area never decreases in classical processes. The third law states that surface gravity cannot be reduced to zero in finite steps. These laws are not mere analogies. They are deep physical truths, confirmed by Hawking's discovery that black holes have genuine temperature and genuine entropy. The thermodynamic nature of black holes provides yet another reason why the center should not contain a singularity. A true singularity, with infinite density and undefined thermodynamic properties, is inconsistent with the well-defined, finite thermodynamics of the black hole as a whole. The exterior has finite temperature, finite entropy, finite energy. The interior cannot have infinite density and remain consistent with the finite exterior. Something must give. And what gives is the singularity. The singularity problem has attracted the best minds in theoretical physics for more than half a century. The proposals they have developed are diverse, creative, and often mutually contradictory. But they share a common conviction. The singularity predicted by general relativity does not exist in nature. It is a placeholder, a signal, a mathematical artifact of a theory applied beyond its domain. What follows is a survey of the most important proposals, each offering a different vision of what replaces the singularity at the center of a black hole. The first major approach is string theory. String theory proposes that the fundamental constituents of nature are not point particles but tiny one-dimensional vibrating strings, roughly the Planck length in size. Different vibrational modes produce different particles. String theory naturally incorporates gravity because one vibrational mode corresponds to the graviton. It unifies gravity and quantum mechanics within a single framework, making it the most developed candidate for a theory of quantum gravity. In string theory, the singularity is resolved because strings have a finite, non-zero size. A point particle can be compressed to infinite density, but a string cannot be compressed below its fundamental length. The string length sets a minimum scale, a floor below which the classical concept of spacetime geometry breaks down and the full stringy physics takes over. The singularity is replaced by a region of Planck-scale stringy physics, complicated and poorly understood but crucially finite. The The most developed string-theoretic proposal for the black hole interior is the fuzzball program, developed primarily by Samir Mather at Ohio State University. In the fuzzball picture, the entire classical interior of a black hole, from the event horizon to the singularity, is replaced by a complicated quantum gravitational structure made of strings and higher-dimensional objects called branes. There is no smooth event horizon. There is no empty interior. There is no singularity. The black hole is a fuzzball, a tangled web of stringy material extending to where the horizon would be. Each distinct fuzzball configuration corresponds to a different microstate of the black hole. For a solar mass black hole, the number of microstates is 10 to the power of 77, matching the Bekenstein-Hawking entropy exactly. This microscopic accounting of entropy is one of the most important achievements of string theory, analogous to Boltzmann's derivation of the entropy of a gas from the counting of molecular configurations. The fuzzball program does for black holes what Boltzmann did for thermodynamics. In the fuzzball picture, there is no information paradox because there is no event horizon in the traditional sense. The fuzzball has a surface, and radiation from that surface carries information about the microstate. Different microstates radiate differently. Information is preserved from the outset. The singularity is eliminated entirely, not softened or resolved, but simply absent. The fuzzball has structure all the way through, and none of that structure involves infinite density. But the fuzzball proposal faces significant challenges. Explicit fuzzball geometries have been constructed only for highly simplified, idealized black holes with high degrees of symmetry. Extending these constructions to realistic astrophysical black holes, non-extremal and rotating, remains an open problem. The fuzzball predicts that a falling observer would encounter the fuzzball structure before crossing the would-be horizon, violating the equivalence principle of general relativity. Whether this is a prediction to be tested or a fatal flaw to be avoided is debated. The numbers are striking. For a supermassive black hole like Sagittarius A star, with roughly 4 million solar masses, the Bekenstein-Hawking entropy is roughly 10 to the power of 87. The number of distinct fuzzball microstates is 10 to the power of 10 to the power of 87. This number is so vast that writing it out in decimal notation would require more digits than there are particles in the observable universe. Each microstate is a different geometric configuration of strings and branes. Each represents a different way the black hole could be internally arranged while looking identical from the outside. The internal complexity is beyond anything in human experience. The second major approach is loop quantum gravity. Unlike string theory, which introduces new fundamental entities, loop quantum gravity starts from general relativity and quantizes spacetime directly. The result is a spacetime that is not smooth and continuous, but is made of discrete, indivisible units at the Planck scale. Space is woven from loops of gravitational field, and geometry emerges from their collective behavior. In loop quantum gravity, the singularity is replaced by a quantum bounce. When matter collapses to extreme densities, approaching the Planck density, the discrete structure of quantum spacetime generates a repulsive quantum gravitational pressure that halts the collapse. The matter reaches a maximum density, the Planck density of roughly 5.1 times 10 to the power of 96 kilograms per cubic meter, and then bounces outward. The infinite density of the classical singularity is replaced by a finite maximum. The distinction between very large and infinite is the distinction between a theory that makes sense and one that does not. The quantum bounce has been studied most extensively in loop quantum cosmology, where it replaces the initial cosmological singularity with a bounce connecting a preceding contracting phase to the current expanding phase. Applied to black holes, the same techniques suggest that the singularity is replaced by a Planck scale core from which matter rebounds. One of the most dramatic predictions of loop quantum gravity is the black-to-white hole transition. The matter that collapsed to form the black hole reaches maximum density at the Planck core, bounces, and begins to expand outward. The black hole eventually transitions to a white hole, a time-reversed black hole from which matter and light emerge. The transition is mediated by quantum gravity and occurs over a timescale that, as measured by an external observer, may be comparable to the Hawking evaporation time. The work of Hal Haggard and Carlo Rovelli, published in 2014, explored this transition in detail. They estimated the geometry of the transition region and the expected timescale. Some researchers have speculated that certain astrophysical transients, brief gamma-ray flashes or fast radio bursts of unknown origin, might be signatures of black-to-white hole transitions. Though this remains highly speculative, loop quantum gravity faces its own challenges. The theory has not been fully developed for realistic four-dimensional spacetime. The dynamics are extraordinarily difficult to solve. Many results come from symmetry-reduced models that may not capture the full complexity of the problem, and the Planck scale, where the predictions become distinctive, is far beyond the reach of any current or foreseeable experiment. The Planck density exceeds the density of matter achievable in particle accelerators by roughly 78 orders of magnitude. The third approach is the holographic principle and the ADS-CFT correspondence. In 1997, Juan Maldacena discovered that a theory of gravity in anti-de Sitter space is exactly equivalent to a quantum field theory, without gravity, living on the boundary of that spacetime, with one fewer dimension. This duality provides the most powerful framework for studying quantum gravity, because it translates gravitational problems into quantum field theory problems. In the ADS-CFT framework, the singularity has a dual description in the boundary theory. The boundary theory is well-defined, unitary, and singularity-free. If the bulk theory is equivalent to the boundary theory, then the singularity in the bulk must be an artifact of the geometric description, not a feature of the fundamental physics. The singularity is resolved in the boundary theory, even though we cannot yet say precisely what the resolution looks like in the bulk. Maldacena's paper has been cited tens of thousands of times, making it the most cited paper in the history of high-energy physics. Within ADS-CFT, the Bekenstein-Hawking entropy is the logarithm of the number of boundary microstates. Information is preserved because the boundary theory is unitary. The evidence that the singularity is resolved within this framework is overwhelming, even though the specific mechanism remains unclear. The Planck star hypothesis, proposed by Carlo Rovelli and Francesca Vidotto, offers a concrete picture of what might replace the singularity within the loop quantum gravity framework. The Planck star is a compact object at the Planck density, with a radius of roughly the Planck length and a mass determined by the total mass of the collapsed matter. It is the densest possible configuration of matter, the quantum gravitational equivalent of the closest packing. The singularity is replaced by a grain of Planck-scale matter, impossibly small, impossibly dense, but crucially finite. The Planck star would be metastable, eventually decaying through a quantum gravitational transition that converts the black hole into a white hole. The matter that collapsed would eventually re-emerge, completing a cosmic cycle of collapse and expansion mediated by quantum gravity at the Planck scale. The singularity is not the end of the story. It is a temporary state, a transition between collapse and expansion, a moment of maximum density from which matter rebounds. The black hole complementarity proposal, introduced by Leonard Susskind, Lars Thorlacius, and John Uglum in 1993, offers yet another perspective on the singularity. Complementarity states that the experience of a falling observer and the experience of an outside observer are both valid descriptions of the same physics, even though they seem contradictory. The outside observer sees information processed on the horizon and returned in Hawking radiation. The falling observer crosses the horizon and falls toward the center. Both descriptions are correct within their own domains, and no single observer can verify both. The relationship between the singularity and the black hole's thermodynamic properties provides additional constraints. The four laws of black hole mechanics, established by James Bardeen, Brandon Carter, and Stephen Hawking, mirror the four laws of thermodynamics. Black holes have genuine temperature, the Hawking temperature, inversely proportional to mass. They have genuine entropy, the Bekenstein-Hawking entropy, proportional to horizon area. Any resolution of the singularity must be consistent with these thermodynamic properties. The exterior has finite temperature, finite entropy, finite energy. The interior cannot have infinite density and remain consistent with the finite exterior. The Penrose process reveals that rotating black holes are dynamic thermodynamic systems, not static objects. Energy can be extracted from the ergosphere. The black hole slows down. Angular momentum is transferred. The singularity sits at the center of a thermodynamic engine whose properties constrain whatever replaces the singularity. The thermodynamic constraints are independent of, and complementary to, the quantum mechanical constraints. Together they form a web of consistency conditions that any resolution must satisfy. The observational constraints from gravitational wave astronomy are also tightening. Each black hole merger detected by LIGO and Virgo tests general relativity in the strong field regime. The ring-down signal tests the no-hair theorem. Future detectors will be sensitive enough to detect subtle deviations, echoes, or anomalies that might signal new physics near the horizon or the center. The Event Horizon Telescope may resolve the photon ring, encoding geometric information about the near-horizon spacetime. Space-based detectors like LISA will detect supermassive black hole mergers across the entire observable universe. The Planck star concept deserves additional attention. If the singularity is replaced by a Planck star, a compact object at the Planck density with a radius of roughly the Planck length, then the center of the black hole contains not a point of infinite density, but the smallest, densest possible grain of matter. This grain would be a quantum gravitational object, governed by the still unknown theory of quantum gravity, with properties we cannot yet calculate precisely. But it would be finite. It would be physical. It would be real in a way that a mathematical singularity is not. The Planck star would contain information. The quantum state of the Planck star would encode the details of everything that fell into the black hole. The information would not be destroyed. It would be compressed, scrambled, encrypted in the quantum degrees of freedom of the Planck scale core, and eventually, through the quantum transition to a white hole, the information would be released back into the universe. The idea of the Planck star connects the singularity problem to the information paradox. If the singularity is replaced by a Planck star that preserves information, then the information paradox is resolved. Information is not destroyed because the singularity does not exist. The information is stored in the Planck star and eventually released through the white hole transition. The two problems, the singularity and the information paradox, are solved simultaneously by the same quantum gravitational mechanism. Each observation narrows the space of possibilities. Each constrains the theories. Each brings us closer to understanding what replaces the singularity. The convergence of theory and observation is slow but real. The gap between what we can calculate and what we can measure is narrowing, and when the two meet, when the theory that resolves the singularity makes a prediction that an observation can test, the question of why the center should not exist will finally have an answer. If complementarity is correct, then the singularity exists only in the falling observer's description. From the outside perspective, all the physics happens on the horizon. The interior, including the singularity, is a complementary description that cannot be independently verified from outside. The singularity exists and does not exist, depending on who is asking. This observer dependence of reality is one of the most radical implications of the singularity problem. The recent discovery of replica wormholes in the gravitational path integral by Jeffrey Pennington, Ahmed Almheri, Thomas Hartmann, Juan Maldacena, and others has provided powerful new evidence that the singularity is resolved in the full quantum theory. The gravitational path integral sums over all possible spacetime geometries. When this sum is performed carefully, including contributions from replica wormhole geometries that connect different copies of the spacetime, the result reproduces the page curve and preserves unitarity. The singularity, which appears in individual classical geometries, is averaged away in the quantum sum. The full quantum theory is singularity-free, even though its classical limit contains singularities. The replica wormhole discovery has additional implications worth considering. In the path integral framework, the quantum theory does not select a single spacetime geometry. It sums over all possible geometries, weighted by their action. Some of these geometries contain singularities, others do not. the physical predictions emerge from the sum, not from any individual geometry. And the sum, when performed correctly, produces finite answers. The singularity is present in some of the individual geometries being summed over, but it is absent from the final, physical result. This is analogous to the way quantum mechanics handles other classically problematic situations. In classical mechanics, a ball rolling toward a barrier either goes over or it does not. In quantum mechanics, the ball is described by a wave function that tunnels through the barrier with some probability. The classical prediction that the ball cannot cross the barrier is wrong. The quantum prediction, which sums over all possible paths including those that tunnel through, gives the correct answer. Similarly, the classical prediction of a singularity may be wrong. The quantum prediction, which sums over all possible spacetime geometries, including those that avoid the singularity, may give the correct answer, no singularity. This is perhaps the most profound insight to emerge from recent research. The singularity is a feature of the classical theory. It is not a feature of the quantum theory. General relativity, a classical theory, predicts the singularity. Quantum gravity, whatever it turns out to be, does not. The singularity is an artifact of the classical approximation, washed out by the quantum effects that the classical theory ignores. But as CFT applies to anti-de Sitter space, which has a negative cosmological constant, our universe has a positive cosmological constant. Whether the holographic principle applies to our universe remains an open and difficult question. The island formula, developed in 2019 and 2020 by Netta Engelhardt, Ahmed Almhiri, Jeffrey Pennington, Henry Maxfield, and others, represents the most significant recent advance. It showed that the entropy of Hawking radiation follows the Page curve, confirming within certain models that information is preserved during black hole evaporation. The calculation works by including quantum extremal islands, regions of the black hole interior that are effectively part of the radiation system. The island formula gives us the answer. Information is preserved. But it does not reveal the mechanism. It does not describe what replaces the singularity. The fourth approach involves emergent spacetime and quantum error correction. Research by Daniel Harlow, Fernando Pastovsky, Benny Yoshida, John Preskill, and others has revealed that the holographic encoding of spacetime has the mathematical structure of a quantum error-correcting code. The three-dimensional bulk is redundantly encoded in the two-dimensional boundary, protected against local errors. Near the singularity, this code degrades. The geometric description becomes unreliable. At the singularity, the code has broken down completely, and the geometric description has no content. Leonard Susskind has proposed that the interior volume of a black hole grows over time, even after thermal equilibrium, and that this growth corresponds to increasing computational complexity. The singularity is the point where the computation exceeds the capacity of the geometric description. The quantum state has become too complex for geometry to capture. The fifth approach is the firewall paradox, and ER equals EPR. In 2012, Ahmed Al-Mahiri, Donald Marolf, Joseph Polchinski, and James Sully showed that three cherished principles, unitarity, the equivalence principle, and the validity of quantum field theory, cannot all hold at the event horizon of an old black hole. If unitarity and quantum field theory hold, the horizon becomes a wall of lethal radiation, a firewall. The smooth crossing predicted by general relativity is replaced by instant annihilation. Susskind and Maldacena responded in 2013 with the ER equals EPR conjecture, proposing that quantum entanglement and wormholes are the same phenomenon. Every entangled pair is connected by a microscopic wormhole. The smooth horizon is maintained by a wormhole network connecting interior to exterior. The singularity might be replaced by a confluence of wormhole geometry rather than a point of infinite density. The sixth approach is causal set theory, which proposes that spacetime is fundamentally discrete, composed of individual atoms of spacetime connected by causal relations. In a discrete spacetime, a point-like singularity cannot form. The collapse reaches a maximum density determined by the fundamental spacing, and the singularity is avoided. A seventh approach is asymptotically safe gravity, initiated by Steven Weinberg in 1979, the gravitational coupling approaches a finite fixed point at high energies. The extreme curvatures near the singularity are tamed, and infinite densities are replaced by finite values. The convergence across all these approaches is remarkable. Every serious proposal for quantum gravity predicts that the singularity is resolved at the Planck scale. The specific mechanisms differ: strings versus loops versus holographic encoding versus discrete sets versus running couplings. But the conclusion is universal. Infinite density does not occur in nature. The Planck scale sets a flaw. The singularity is replaced by something finite. The math is striking. The Planck density is roughly 5.1 times 10 to the power of 96 kilograms per cubic meter. The Planck length is roughly 10 to the power of negative 35 meters. The Planck time is roughly 10 to the power of negative 43 seconds. These are the natural units of quantum gravity, formed from the three fundamental constants: Newton's gravitational constant, the speed of light, and Planck's reduced constant. Every approach to the singularity identifies the Planck scale as the boundary between the classical regime, where general relativity works, and the quantum regime, where it does not. The singularity is a classical prediction. The Planck scale is where the classical prediction breaks down and the quantum prediction takes over. The thermodynamic constraints are equally powerful. The four laws of black hole mechanics, established by James Bardeen, Brandon Carter, and Stephen Hawking in the early 1970s, mirror the four laws of thermodynamics. The Hawking temperature of a solar mass black hole is roughly 60 billionths of a Kelvin. The evaporation time is roughly 10 to the power of 67 years. Any resolution of the singularity must be consistent with these thermodynamic properties. The thermodynamics provides a cross-check that every proposal must satisfy. There is a common thread running through all of these approaches. Every serious candidate for quantum gravity resolves the singularity at the Planck scale. The mechanisms differ. Strings versus loops versus holographic encoding versus discrete causal sets versus running couplings. But the endpoint is the same. The Planck density is the flaw. Infinite density does not occur. The singularity is replaced by something finite. This convergence of independent approaches is one of the strongest pieces of theoretical evidence available about the center of a black hole. Independent lines of reasoning, starting from different assumptions, using different mathematical techniques, developed by physicists with different theoretical commitments, all arrive at the same conclusion. The singularity is not real, it is a signal, and the signal says the classical theory has been pushed past its breaking point. The gravitational path integral, a technique for summing over all possible spacetime geometries, provides additional support. Recent work by Jeffrey Pennington, Ahmed Almheri, Thomas Hartman, Juan Maldacena, Edgar Shagulian, and Amir Hossein Tajdini showed that the path integral naturally includes contributions from replica wormholes, spacetime geometries that tunnel through or around the singularity. When all contributions are summed, the result is finite and unitary. The singularity is washed out by the quantum sum. Individual classical spacetimes contain singularities, but the full quantum theory, which sums over all spacetimes, does not. This is a profound shift in perspective. The singularity is a feature of individual classical solutions. It is not a feature of the full quantum theory. The quantum theory averages over all possibilities, including possibilities that avoid the singularity. The result is a finite, well-defined prediction, even at the center of a black hole. The black hole merger observations from LIGO and Virgo provide empirical constraints. Each merger produces gravitational waves whose waveform encodes information about the spacetime geometry. The ringdown phase tests the no-hair theorem. So far, every observation is consistent with general relativity. No deviations have been detected. But future, more sensitive detectors may detect echoes or anomalies in the ringdown signal that could provide indirect evidence about the nature of the interior. The Event Horizon Telescope provides another observational window. Future observations may resolve the photon ring, a sharp bright feature near the event horizon that encodes geometric information about the near-horizon spacetime. If quantum gravity modifies this geometry, the photon ring might carry the signature. The black hole mergers observed by LIGO and Virgo have confirmed that the exterior of black holes obeys general relativity with extraordinary precision. The waveforms match theoretical templates to remarkable accuracy. The ring-down frequencies match the predictions of the no-hair theorem. No deviations have been detected. This tells us that general relativity is correct outside the event horizon. It does not tell us what happens inside, but it constrains the quantum gravitational modifications. Any modification to the interior must be consistent with the unmodified exterior. The quantum gravity effects must be confined to the Planck scale near the center, invisible from the outside, consistent with the precision tests that general relativity has already passed. This observational constraint is powerful. It rules out proposals that modify the exterior geometry. It demands that quantum gravitational effects be localized near the center, affecting only the Planck scale region where the singularity would otherwise form. The exterior must be standard general relativity. The interior must be quantum gravity. And the transition between the two must be smooth, occurring gradually as curvature approaches the Planck curvature. The convergence is the most important lesson from the study of the singularity. Independent approaches, starting from different assumptions, using different mathematics, developed by researchers with different theoretical commitments, all arrive at the same conclusion. The singularity is not real. It is resolved at the Planck scale. Infinite density does not occur. The replacement is finite, quantum, and consistent with the preservation of information. This convergence gives us confidence even in the absence of direct experimental verification. When independent lines of evidence agree, the probability that they are all wrong decreases rapidly. The convergence of all serious quantum gravity proposals on the resolution of the singularity at the Planck scale is strong theoretical evidence, perhaps the strongest we can obtain in the absence of Planck scale experiments. And this is where the answer becomes deeply unsettling, because the convergence tells us that the singularity is resolved, but it does not tell us how. The what is clear. The how remains the deepest mystery in physics. The deeper truth about why the center of a black hole should not exist is that the singularity reveals a fundamental flaw, not in our equations, but in our conception of reality. The singularity is not just a mathematical problem. It is a conceptual problem, and the resolution will require not just new equations, but new ideas, new categories, new ways of thinking about what space, time, and existence actually are. The most profound insight to emerge from the study of the singularity is that spacetime may not be fundamental. This idea, once radical, has gained increasing support from multiple independent lines of evidence within the ADS, CFT correspondence, quantum error correction, and the study of entanglement. If spacetime is not fundamental, if it emerges from something deeper, then the singularity is not a tear in the fabric of reality. It is a failure of the emergent description. Just as temperature is an emergent property of molecular motion that breaks down at the level of individual molecules, spacetime may be an emergent property of quantum information that breaks down at the Planck scale. The singularity is the point where the emergence fails. The geometric description of reality, the description in terms of smooth, continuous spacetime, can no longer be sustained. The underlying quantum reality continues, smooth and unitary, but the geometric projection has lost coherence. Let that sink in. Space and time, the two categories that underpin all of human experience, all of physics, all of our intuitions about what it means for something to exist, may not be fundamental. They may be projections, approximations, coarse-grained descriptions of an underlying reality that is purely informational, purely quantum mechanical, and has no intrinsic spatial or temporal structure. The universe may not live in space and time. Space and time may live in the universe, emerging from quantum information and entanglement as emergent phenomena. The evidence for this view comes from several directions. The Bekenstein-Hawking entropy formula tells us that the information content of a black hole is proportional to the area of its horizon, not its volume. If the fundamental degrees of freedom were distributed through the three-dimensional volume, the entropy would scale with volume. The fact that it scales with area is the holographic principle, the idea that the three-dimensional bulk is a projection of two-dimensional boundary physics. The interior, including the singularity, may be less fundamental than the boundary. Mark van Ramsdonk showed in 2010 that in the ADS-CFT framework, reducing the entanglement between two regions of the boundary theory causes the corresponding bulk spacetime to disconnect. No entanglement, no spacetime. Space is held together by quantum correlations. The fabric of reality is woven from entanglement. When the entanglement is disrupted, space falls apart. Near the center of a black hole, the entanglement structure that gives rise to smooth geometry is maximally disrupted. The quantum state is maximally scrambled. The information is distributed across the horizon in patterns of extreme complexity. The geometric description, the emergent spacetime, has broken down. There is no center in the geometric sense because geometry has ceased to be valid. This perspective transforms the question of why the singularity should not exist. The singularity should not exist because it is a feature of a description that has exceeded its range of validity. It is like asking what happens to the temperature of a gas when you reach a single molecule. The question is not wrong, exactly, but it reveals that the concept of temperature is emergent, valid only for large collections of molecules, and ceases to apply at the level of individual molecules. Similarly, the concept of spacetime geometry is emergent, valid for regions of moderate curvature, and ceases to apply at the Planck scale. Let that sink in. The connection between entanglement and geometry has been further developed through the concept of quantum error correction. The holographic encoding of spacetime, as shown by Harlow, Pestovsky, Yoshida, and Preskill, has the structure of a quantum error-correcting code. Bulk spacetime is redundantly encoded in the boundary, protected against local disturbances. This redundancy is why spacetime is robust, why it maintains its structure despite small perturbations. But, at the singularity, the code has degraded beyond repair. The encoding has broken down. The geometric description has no content. What remains is the boundary theory, evolving smoothly and unitarily, but the three-dimensional projection it normally generates has dissolved. The computational complexity perspective adds another layer. Suskind's proposal that the interior volume of a black hole grows in proportion to the computational complexity of its quantum state suggests that the singularity is the limit of geometric representation. The quantum state has explored more of its configuration space than any geometric picture can represent. The computation has outrun the geometry. The map can no longer represent the territory. The connection between the singularity and the nature of time itself is one of the deepest aspects of the problem. Inside a non-rotating black hole, the singularity is a future moment, not a spatial location. The radial direction has become time-like. The singularity is in the future of every particle inside the event horizon, as inevitable as next Thursday. You cannot avoid it, you cannot steer around it, you cannot slow your approach, every path leads to it. If the singularity does not exist, if it is replaced by a quantum bounce or a Planck scale core, then what replaces the future moment? In the loop quantum gravity picture, the singularity is replaced by a bounce, a transition from collapse to expansion. The future is not a dead end, but a doorway. The matter does not end at the singularity. It passes through the Planck scale transition and emerges, expanding outward, potentially forming a white hole. The arrow of time does not terminate, it reverses. This has profound implications for the nature of time itself. If the singularity is the end of time, then time has a boundary, a final moment beyond which nothing exists. If the singularity is replaced by a bounce, then time continues, flowing from collapse to expansion, from black hole to white hole, from past to future, and through a quantum bridge that connects them. The nature of time at the center of a black hole is one of the deepest open questions in physics. The concept of the Planck star, proposed within the loop quantum gravity framework, offers a concrete picture of what might replace the singularity. The Planck star is a compact object at the Planck density, with a radius of roughly the Planck length. It is the densest possible configuration of matter, the quantum gravitational equivalent of maximum packing. The singularity is replaced by a grain of Planck-scale matter, tiny beyond imagination, dense beyond comprehension, but finite. The Planck star is metastable, eventually decaying through a quantum transition that converts the black hole into a white hole. The collapsed matter rebounds and emerges, completing a cycle from collapse to expansion mediated by quantum gravity. If the Planck star picture is correct, then the center of a black hole is not empty, not infinite, not undefined. It is a physical object, the smallest and densest possible, governed by quantum gravity, preserving information, obeying the laws of thermodynamics, and eventually releasing its contents back into the universe. The singularity is replaced by a seed, a kernel of quantum gravitational matter from which the white hole will someday grow. The connection between black hole complementarity and the singularity adds another layer. If complementarity is correct, the singularity exists only in the falling observer's description. From the outside perspective, all physics happens on the horizon. The interior is a complementary description that cannot be independently verified. The singularity exists and does not exist, depending on who is asking. This observer dependence of reality is one of the most radical implications of the singularity problem, and represents a departure from the classical ideal of a single, objective, observer-independent reality. The connection between the ER equals EPR conjecture and the singularity is also important. If entanglement and wormholes are the same phenomenon, the interior of the black hole is connected to the exterior through a vast network of microscopic wormholes. The singularity might be replaced by a confluence of this wormhole geometry, a point of maximum connectivity rather than a point of infinite density. The center would be not the end of space, but a hub in a quantum network connected to the outside through entanglement, linked to the Hawking radiation through wormhole geometry. The thermodynamic arrow of time, defined by the direction of increasing entropy, points toward black holes. Black holes are the maximum entropy objects for a given mass. The total entropy of all black holes dominates the entropy of the cosmos. When matter falls into a black hole, the entropy of the universe increases by the Bekenstein-Hawking entropy, an enormous number. The singularity, if it existed, would be the final destination of the thermodynamic arrow, the end point of entropy maximization. But the singularity should not exist. Something finite must replace it. And that something must be consistent with the thermodynamic arrow, with the second law, with the information-preserving demands of quantum mechanics. The connection to computational complexity adds yet another dimension. Susskind's conjecture that the interior volume grows in proportion to computational complexity suggests that the center is not static but dynamic. The interior stretches, the space deepens, the distance from horizon to center increases over time. The singularity is the limit of this growth, the point where complexity exceeds the capacity of geometric description. The center of the black hole is not a fixed point. It is a moving frontier, the edge of the computable, the boundary of what geometry can express. If this picture is correct, the singularity is not a physical entity. It is a computational limit. It is the point where the quantum state has become too complex for any geometric representation. The center is not infinite. It is indescribable, at least in the language of space-time geometry. A different language, the language of quantum information, can describe it, but the geometric language cannot. The scrambling time of a black hole provides a concrete measure of how fast information is processed near the center. For Sagittarius A star, the scrambling time is on the order of milliseconds. Within thousandths of a second, information that falls in is distributed across the entire horizon. Patrick Hayden and John Preskill showed in 2007 that black holes saturate the fundamental quantum bound on scrambling speed. No physical system can scramble information faster. This is not science fiction. These are rigorous results derived within well-defined mathematical frameworks. The Bekenstein-Hawking entropy formula provides another crucial window into why the center should not exist. The formula, S equals A over 4 in Planck units, tells us that the information content of a black hole is proportional to its surface area, not its volume. If the internal degrees of freedom were distributed uniformly through the three-dimensional volume, entropy would scale with volume. The fact that it scales with area is the holographic principle in action. The three-dimensional interior is a projection of two-dimensional boundary physics. The singularity, which is at the center of the three-dimensional interior, may be a feature of the projection rather than of the underlying reality. When the projection breaks down, the singularity dissolves. For a solar mass black hole, the entropy is roughly 10 to the power of 77. The number of microstates is 10 to the power of 10 to the power of 77. This vast number represents the internal complexity of the black hole, the number of different configurations it can occupy while looking identical from the outside. Any resolution of the singularity must account for this complexity. Any replacement must have enough degrees of freedom to support this many configurations. A true singularity, a point of zero volume, cannot accommodate any microstates at all. The entropy demands structure. The singularity denies it. The entropy wins. The scrambling time tells us how fast the black hole processes information. For Sagittarius A star, it is on the order of milliseconds. Patrick Hayden and John Preskill showed that black holes saturate the fundamental quantum bound on scrambling speed. The black hole is the fastest information processor in nature. The singularity, or whatever replaces it, is the computational engine that drives this processing. The center is not a point of destruction, but a point of maximum computational activity. The Margulis-Levitin theorem sets a fundamental limit on how fast any quantum system can evolve between orthogonal states. The limit is determined by the energy of the system. A black hole with its enormous mass energy operates right at this limit. It processes information at the fastest rate permitted by quantum mechanics. The center of the black hole is where this maximum rate processing occurs. The connection between the singularity and the arrow of time deepens the picture further. Black holes are the objects of maximum entropy for a given mass. The total entropy of all black holes in the observable universe is estimated at roughly 10 to the power of 104, dwarfing the entropy of all non-black hole matter at roughly 10 to the power of 88. The entropy of the cosmos is dominated by black holes. The arrow of time, the direction of increasing entropy, points toward black holes. The singularity, or whatever replaces it, is the ultimate thermodynamic destination. Roger Penrose has argued that the low entropy of the early universe is connected to the gravitational field. As the universe ages, gravity organizes matter into clumps, stars, galaxies, and black holes, each step increasing the entropy. Black holes represent the maximum entropy state. The singularity is where the arrow of time reaches its target, but the singularity should not exist because quantum mechanics demands finite entropy, finite density, finite information content. The arrow of time points toward the center of a black hole, but when it arrives, it finds not infinite density but a Planck-scale quantum core, a region of maximum but finite entropy, the end point of the thermodynamic journey. Black hole complementarity, proposed by Leonard Susskind, Laurus Thorlacius, and John Uglum in 1993, adds yet another dimension. It states that the experience of a falling observer and the experience of an outside observer are both valid descriptions of the same physics. The outside observer sees information absorbed by the horizon and returned in Hawking radiation. The falling observer crosses the horizon and falls toward the center. Both are correct, neither is complete, and no single observer can verify both. If complementarity is correct, then the question of whether the singularity exists depends on who is asking. For the outside observer, the center does not exist as an independent entity. The information is on the horizon. For the falling observer, the center is whatever quantum gravity says replaces the singularity. Reality, at this level, becomes observer-dependent, and the singularity, which should not exist according to quantum mechanics, may also not exist according to the outside observer's description. It exists only in the falling observer's complementary description, a description that can never be communicated to the outside. The deeper truth, then, is this. The center of a black hole should not exist because the concept of center presupposes a geometric description that is not fundamental. The center is a feature of the emergent spacetime, the three-dimensional projection that normally works so well but that fails at the Planck scale. When the projection fails, the center dissolves. What remains is not a point of infinite density but a pattern of quantum information, encoded on the boundary, evolving unitarily, preserving all information, and generating the illusion of a three-dimensional interior that works everywhere except at the place we call the center. The picture that emerges from all of these considerations is one of remarkable coherence. The singularity should not exist because the Heisenberg uncertainty principle forbids infinite compression. Because unitarity forbids the destruction of information. Because the holographic bound demands finite internal structure. Because the thermodynamics demands finite entropy and temperature. Because the emergent nature of spacetime means the geometric description fails before infinite density is reached. Because every candidate theory of quantum gravity replaces the singularity with something finite at the Planck scale. Because the gravitational path integral averages away the singularity in the quantum sum. Each of these reasons is independent. Each comes from a different principle, a different framework, a different line of reasoning, and they all point in the same direction. The singularity should not exist. And, in the deepest sense available to current physics, it probably does not. What does it mean that the most common extreme objects in the universe contain, at their centers, a prediction that should not be true? What does it mean for our understanding of nature, of knowledge, of our place in a cosmos that seems determined to push our comprehension to its limits and then beyond? It means, above all, that we live in a universe deeper than we imagined. The surface layer, the layer of space-time and classical geometry, works extraordinarily well for everyday physics. It describes the bending of light by massive objects. It predicts the orbits of planets. It explains the expansion of the universe. It guided the detection of gravitational waves. This surface layer is powerful and precise. But it is not the bottom. Beneath it lies something else, something quantum, something informational, something that we glimpse only at the extremes, only at the Planck scale, only at the center of a black hole. There is a pause required here, a philosophical pause, because the singularity is not just a physics problem, it is a statement about the limits of human knowledge. Can we, finite minds living in a universe of moderate conditions, understand the physics of the Planck scale? Can we comprehend a reality that is not spatial, not temporal, not geometric? Can we build the mathematical tools needed to describe something that has no analog in everyday experience? The history of physics suggests that we can. The atomic theory was developed by beings made of atoms. Quantum mechanics, which defies everyday intuition at every turn, was developed by beings whose everyday experience is entirely classical. General relativity, which describes the curvature of four-dimensional spacetime, was developed by beings who experience three spatial dimensions and one temporal dimension. In each case, human minds transcended their own experiential limitations to grasp a deeper layer of reality. The singularity demands the same transcendence. The theory that resolves it, quantum gravity, will describe a reality that has no spatial or temporal structure at the fundamental level. It will describe a world of quantum information and entanglement from which space, time, and geometry emerge as approximate, large-scale descriptions. Grasping this theory will require mathematical intuitions that do not yet exist, conceptual categories that have not yet been invented, and frameworks of thought that no one has yet imagined. But the attempt to understand is itself a monument to what makes us human. The singularity does not care whether we understand it. The universe is not waiting for our comprehension, but we are reaching for it anyway, not because the universe demands it, but because we demand it of ourselves. The practical implications of the singularity problem have been substantial. The mathematical tools developed to study black hole singularities have found applications across physics. Quantum error correction, inspired by the holographic structure of spacetime, is essential for building fault-tolerant quantum computers. The thermodynamics of black holes has illuminated the physics of strongly interacting quantum systems. The AD-CFT correspondence has been applied to problems in condensed matter physics, nuclear physics, and fluid dynamics. Gravitational wave astronomy has opened an entirely new observational window onto the universe. The study of the singularity has driven connections between physics and other fields that no one anticipated. The topological methods Penrose used in his singularity theorem drew on pure mathematics and transformed both fields. The holographic principle connects gravity to information theory. The ADES CFT correspondence connects gravity to quantum field theory and has been applied to problems in condensed matter physics, nuclear physics, and fluid dynamics. The connection between entanglement and geometry has inspired new approaches in quantum computing. The error-correcting structure of spacetime has applications in quantum information science. Each of these connections was unexpected. Each was driven by the singularity problem. The singularity has been a catalyst for interdisciplinary collaboration on a scale rarely seen in science. General relativists, particle physicists, string theorists, loop quantum gravity researchers, mathematicians, computer scientists, and information theorists have all been drawn to the same fundamental problem. The result has been a flowering of ideas that extends far beyond the original question. Consider what it means that the study of the singularity has generated practical technologies. Quantum error correction, essential for building fault-tolerant quantum computers, was directly inspired by the holographic encoding of spacetime discovered in the study of black holes. The mathematical tools developed for the ADES CFT correspondence have been applied to problems in materials science, nuclear physics, and fluid dynamics. The thermodynamics of black holes has illuminated the physics of strongly interacting quantum systems, from quark-gluon plasmas created at particle accelerators to the exotic states of matter found in neutron stars. The singularity problem has also driven collaboration across disciplinary boundaries. General relativists work with particle physicists. String theorists work with condensed matter physicists. Mathematicians work with computer scientists. The result is a cross-pollination of ideas that has enriched every field involved. The most abstract and seemingly impractical question in physics, what is at the center of a black hole, has proven to be one of the most productive sources of new ideas and new tools in modern science. The philosophical implications are equally significant. The singularity forces us to confront the question of whether mathematical description is sufficient for understanding nature. For 3 centuries, physics has progressed by writing better equations. The singularity is a place where the equations fail. Does this mean nature fails? Or does it mean our mathematical language needs to be expanded? Most physicists believe the latter, that a better mathematical language, the language of quantum gravity, will describe the center without producing infinities. The failure is in our tools, not in the universe, and the history of physics gives us every reason to believe that better tools will be found. Every previous infinity in physics, from the ultraviolet catastrophe to the infinities of quantum field theory resolved by renormalization, has been a signal of incomplete theory rather than a feature of nature. The singularity will likely follow the same pattern. The infinity is a signal. The signal says, your theory is incomplete. A better theory exists. And that better theory will replace the infinity with something finite, just as quantum mechanics replaced the ultraviolet catastrophe with quantized radiation, and just as renormalization replaced the infinities of quantum field theory with finite, measurable predictions. The observational landscape is evolving rapidly. The LIGO-Virgo-Cagra network has detected roughly 90 gravitational wave events. Each tests general relativity in the strong field regime. Future detectors, including the Einstein Telescope and Cosmic Explorer on the ground and LISA in space, will push the sensitivity much further. The Event Horizon Telescope continues to improve, adding new stations and new frequencies. Future iterations may resolve the photon ring, providing geometric information about the near-horizon spacetime that could constrain models of the interior. Each new observation tightens the constraints on quantum gravity proposals. Each narrows the range of possible resolutions of the singularity. The gap between theory and observation is narrowing, slowly but measurably. The answer to why the center should not exist, and what exists in its place, is being approached from both the theoretical and observational sides. When the two sides meet, the singularity problem will finally be solved. The next generation of physicists will have tools that we can barely imagine. Quantum computers, capable of simulating aspects of quantum gravity. Gravitational wave detectors sensitive enough to measure near-horizon quantum effects. Space-based interferometers capable of unprecedented precision. Theoretical frameworks more refined and more constrained by data than anything available today. The resolution of the singularity may come not from a single breakthrough but from the gradual convergence of observation, computation, and theory over decades. The next generation of observations will push our understanding further. Future gravitational wave detectors will detect subtle deviations from general relativity that might constrain the structure of the black hole interior. The Event Horizon Telescope will produce sharper images that might reveal quantum gravitational effects near the horizon. Space-based detectors like LISA will detect supermassive black hole mergers. Each observation constrains the theories, each narrows the possibilities, each brings us one step closer to understanding why the center should not exist and what exists in its place. The relationship between abstract theory and practical technology continues to strengthen. The mathematical tools developed for the singularity problem have applications in quantum computing, cryptography, materials science, and artificial intelligence. Quantum error correction, inspired by the holographic encoding of spacetime, is essential for building fault-tolerant quantum computers. The connection between entanglement and geometry has opened new approaches in quantum chemistry. The thermodynamics of black holes has illuminated the physics of strongly coupled quantum materials, from quark-gluon plasmas to high-temperature superconductors. The singularity problem, the most abstract and seemingly impractical question in all of physics, has generated a cascade of practical innovations. The darkness at the center of a black hole has illuminated corners of science that seem at first glance to have nothing to do with gravity or cosmology. This is one of the most remarkable features of fundamental physics. The most abstract questions often generate the most practical answers. The philosophical implications deserve attention as well. The singularity forces us to confront the limits of mathematical description. For 3 centuries, the success of mathematical physics suggested that the universe is fundamentally mathematical, that every physical process can be captured by equations. The singularity challenges this assumption. It is a place where the equations produce infinity, where the mathematical description fails. Does this mean that nature itself breaks down, or does it mean that our mathematical language is not rich enough? Most physicists believe the latter. They believe that a better mathematical language, the language of quantum gravity, will describe the center of a black hole without producing infinities. The singularity is a failure of the language, not a failure of nature. Nature does not produce infinities. Nature continues, smooth and self-consistent, through the region that our current equations cannot describe. The failure is in our tools, not in the universe. And the history of physics gives us every reason to believe that better tools will be found. Every previous infinity in physics, from the ultraviolet catastrophe to the infinities of quantum field theory, resolved by renormalization, has been a signal of incomplete theory rather than a feature of nature. The singularity will likely follow the same pattern. The infinity is a signal. The signal says, your theory is incomplete. A better theory exists. And that better theory will replace the infinity with something finite, just as quantum mechanics replaced the ultraviolet catastrophe with quantized radiation, and just as renormalization replaced the infinities of quantum field theory with finite, measurable predictions. The observational landscape is evolving rapidly. The LIGO-Virgo-Cagra network has detected roughly 90 gravitational wave events. Each tests general relativity in the strong field regime. Future detectors, including the Einstein telescope and Cosmic Explorer on the ground and LISA in space, will push the sensitivity much further. The Event Horizon Telescope continues to improve, adding new stations and new frequencies. Future iterations may resolve the photon ring, providing geometric information about the near-horizon spacetime that could constrain models of the interior. Each new observation tightens the constraints on quantum gravity proposals. Each narrows the range of possible resolutions of the singularity. The gap between theory and observation is narrowing. slowly but measurably. 2. The answer to why the center should not exist and what exists in its place is being approached from both the theoretical and observational sides. When the two sides meet, the singularity problem will finally be solved. Each brings us closer to understanding why the center of a black hole should not exist and what exists in its place. The singularity problem has also driven unexpected connections between physics and other fields. The connection between spacetime and quantum information has inspired new approaches in quantum computing. The holographic principle has influenced thinking in mathematics, philosophy, and even cognitive science. The question of what spacetime is made of, forced upon us by the singularity, has opened lines of inquiry that extend far beyond physics. We stand at a remarkable moment. The tools are improving, the theories are converging, the observations are constraining. The answer is not yet in hand, but the outlines are emerging. And the answer, when it comes, will not merely resolve the singularity, it will tell us what spacetime is made of. It will tell us what reality is at the deepest level. It will connect the physics of the very large to the physics of the very small. It will unify gravity with the other fundamental forces. It will explain why spacetime has 4 dimensions, or whether the number of dimensions is itself emergent. It will resolve not only the singularity at the center of a black hole, but also the initial singularity that cosmological models predict for the very early universe. The two singularities, the cosmological and the black hole, are the same problem in different temporal clothing. Resolving one will resolve the other. It will answer the question that the singularity has been asking, silently and patiently, from the center of every black hole since the first one formed. The center of a black hole should not exist. This is not a statement of philosophical preference. It is the conclusion of rigorous physics supported by the foundational principles of quantum mechanics, the most precisely tested theory in the history of science. The Heisenberg uncertainty principle says infinite density is impossible. Unitarity says information cannot be destroyed at a singularity. The holographic bound says the internal structure must be finite. The third law of thermodynamics says the entropy must be well defined. Every principle of quantum mechanics that has ever been tested, every prediction that has ever been confirmed, points in the same direction. The singularity is not real. And yet general relativity, the most successful theory of gravity ever written, says it must be there. The Penrose-Hawking singularity theorems guarantee it under very general conditions. The mathematics is airtight. The logic is impeccable. The conclusion is unavoidable. 2 theories, 2 conclusions, 1 contradiction. The resolution of this contradiction is the most important unsolved problem in physics. It will require a theory of quantum gravity, a theory that merges the insights of general relativity and quantum mechanics into a single, coherent, finite framework. Every candidate for this theory, from string theory to loop quantum gravity to holographic dualities to causal set theory, agrees on one thing: the singularity is resolved. Infinite density does not occur. The Planck scale sets a flaw. Something finite and well-defined replaces the classical prediction of infinity. The center of a black hole should not exist because spacetime is not fundamental. It is emergent. It arises from quantum information and entanglement. And at the center of a black hole, the emergence breaks down. The geometric description fails. The 3-dimensional projection dissolves. What remains is the underlying quantum reality, smooth and unitary, preserving all information, but no longer expressible in the language of spacetime geometry. The singularity is the most profound signal in all of physics. It is the universe telling us, with mathematical precision, that our understanding is incomplete. It is a flashing red light in the equations, a warning that the current framework has been pushed past its limits, an invitation to discover the deeper framework that lies beneath. Every great revolution in physics has been triggered by a similar signal. The ultraviolet catastrophe led to quantum mechanics. The incompatibility of Maxwell's equations with Galilean relativity led to special relativity. The incompatibility of Newtonian gravity with special relativity led to general relativity. And now the singularity, the incompatibility of general relativity with quantum mechanics, is leading us toward quantum gravity. The center of a black hole should not exist, and in the deepest sense available to current physics, it probably does not. What exists in its place, what the quantum reality looks like beneath the failed geometric projection, is the question that will define the next era of physics. It is the question that connects everything: gravity and quantum mechanics, information and geometry, entropy and time, the very large and the very small. The history of physics is a history of revolutions triggered by failures. Classical electromagnetism failed to describe the spectrum of hot objects, and quantum mechanics was born. Newtonian mechanics failed at the speed of light, and special relativity was born. Newtonian gravity failed at the precision of Mercury's orbit, and general relativity was born. Each failure was not an ending but a beginning, not a defeat but an invitation. The singularity is the latest invitation, and the revolution it triggers will be the deepest yet. The singularity is perhaps the most patient mystery in the cosmos. It has been there since the first black hole formed. It has been there through every observation, every calculation, every debate. It waits behind the event horizon, silent and absolute, for the theory that will finally explain it. And when that theory comes, it will not merely resolve a technical problem in mathematical physics. It will reveal the deepest truth about the nature of reality. It will tell us what space and time are made of. It will tell us what it means for something to exist. The search for this theory has been one of the great intellectual adventures of the past century. It has attracted the brightest minds in physics, from Einstein to Hawking to Penrose to Maldacena to Susskind. It has generated some of the most beautiful mathematics ever written, and it has produced insights that have transformed our understanding of gravity, quantum mechanics, thermodynamics, information, and the nature of spacetime. Every previous revolution changed what we know about the universe. This one will change what we know about the fabric of the universe itself. It will tell us whether space and time are fundamental or emergent. It will tell us whether the three-dimensional world we perceive is the bottom layer of reality or a holographic projection. It will tell us what information is, at the most basic level, and how it relates to existence itself. Somewhere, right now, a physicist is working on this question. Perhaps they are scribbling equations on a whiteboard. Perhaps they are running a simulation on a supercomputer. Perhaps they are lying awake at 3 a.m, turning an idea over and over, sensing that something is almost within reach. The singularity does not care who finds the answer. It does not care when. It has been waiting since the first black hole formed. It will wait until the theory is ready, and when the theory comes, the singularity will yield, the infinity will become finite, the breakdown will become a transition. The center of the black hole will be revealed not as a point of infinite density, but as a window into the deepest structure of reality, a place where the emergent description of spacetime dissolves and the fundamental quantum reality shows through. The center of a black hole should not exist, and the day we understand why, truly understand, with a complete theory that replaces the singularity with something finite and comprehensible, will be the day we finally know what the universe is made of. That day has not yet come, but the question is clear, the tools are sharpening, the theories are converging, and the singularity, patient and silent at the center of every black hole, is waiting for the mind that will finally explain why it should not, and does not, exist. The center of a black hole should not exist. And this realization, this confrontation between what our best theories predict and what our deepest principles demand, is the most productive contradiction in the history of science. Every attempt to resolve it has generated new insights. Every failed approach has eliminated possibilities and narrowed the search. Every new mathematical tool developed for the singularity problem has found applications in other fields. The resolution will come. It may come from string theory, which replaces the singularity with a fuzzball. It may come from loop quantum gravity, which replaces it with a quantum bounce. It may come from the holographic principle, which reveals it as a breakdown of emergent geometry. It may come from an approach that no one has yet imagined, a framework so different from our current thinking that we cannot predict its shape from here. But when it comes, it will answer more than the question of what is at the center of a black hole. It will answer the question of what spacetime is made of. It will answer the question of what reality is at the deepest level. It will connect gravity to quantum mechanics, information to geometry, entropy to time, computation to existence. It will be the capstone of 3 centuries of physics, the final piece in the puzzle that began with Newton and continued through Maxwell, Einstein, Bohr, Heisenberg, Dirac, Hawking, and Penrose. The center of a black hole should not exist, and in that should not lies the most important word in all of physics, because should not means the current theory is wrong, and wrong means there is something better, something deeper, something truer, something waiting to be found. The answer will not come easily. It never does in physics. Quantum mechanics took nearly 3 decades to develop, from Planck's first quantum in 1900 to the complete quantum field theory of the 1940s. General relativity gestated for 8 years in Einstein's mind. Quantum gravity has been in development for more than half a century, and the end is not yet in sight, but the progress is real. The tools are improving, the observations are accumulating, the constraints are tightening, and the theoretical insights, from holography to entanglement to error correction to computational complexity, are converging toward an answer that, when it arrives, will be recognized not just as a solution to the singularity problem, but as the deepest truth about the nature of existence. The search continues, the darkness patiently waits, and the answer, when it comes, will illuminate absolutely everything.